Hello. Howdy, everyone. All right, welcome to another video. One of the first ones I'm doing. EE221, Intro to MATLAB. This is an optional video that I wanted to do for you all, for those who are curious about why I'm all of a sudden been talking about MATLAB. Like, what is this MATLAB that David's been recommending me? So, MATLAB is well, to tell a quick little history. So, MATLAB is called, or stands for Matrix Laboratory, or laboratories, and it was basically created because a couple engineers were like, oh yeah, Excel's great, but we kind of want to do more with data and try to process more matrices. So MATLAB was born to basically be a tool that engineers can use to do a lot of powerful computations, store data, etc. You can do a lot of things with MATLAB. So for the purpose on EE221, I just want to get like a small introduction, not too crazy. You'll probably go into depth. If you're an electrical engineer, you're going to go into depth in EE360, which is taught, if you guys take it next semester, you can take it with a couple of the professors here at UNLV. So for now, I just want to talk about, well, what MATLAB is and what we can do. So here you can see, yes, the background right here is MATLAB. And we can, if you're downloading this for the first time, you're going to see, oh, there's some setups and other things to do. But assuming you purchased MATLAB legally and got it all up and running, make sure your specs match. This is what you'll see. You'll just see a blank screen and it'll say, oh, student license, and you got stuff ready. As you can see, I have cool stuff right here. For now, if you're trying to start MATLAB for the first time, don't worry. It kind of looks like a programming language, but I'm going to tell you now, treat it as just a big fat calculator, just big, and it does numbers. Like if you want me to do something like 1 plus 1, 2, or what about 3 times 3? You see, does stuff. Ooh, what if I want to do A is equal to 4? Oh, look, you see numbers pop up, and that's how it stores stuff. Actually, let me change my preferences for you guys. Maybe you guys are saying, hey, I can't see those letters, David. Don't worry, I am here to help you. Oh wait, that's the other way around. There we go, now you can all see that. Boom. B is equal to 5. See, here's our matrices. You see, it's like Excel, but bigger. So let me see, exit out of there. And what if I do C is equal to A plus B? Really cool, right? Or what about C is equal to A minus B? Really simple stuff. You can do a lot of things. If you have MATLAB on your laptop, you can literally be like, I don't need a TI. Just do computational stuff. But I'm trying to go really brief for those who are scared of using MATLAB. Don't worry, it's literally a calculator. Let's go to the gist of what I'm going to try and do. Actually, practically, I don't want to waste too much time on this. There we go. It's dock. Oh, there we go. Dock to the screen. And if you wanted to see quick matrices, this is the reason why it's called Matrix Laboratory. 1, 2, this semicolon right here gives us another, initiates a new column, 3, 4. We do this. If I, what I did was I controlled entered. You can also run section, or you can run. And then, you see I have stuff already saved up. Oh, hidden stuff for a surprise. EE221. There we go. We can call this one EE221 exercise 1. There we go. And then it's going to ask you to change folder. This is the biggest common mistake that everyone does, and they don't change the folder, or they click add to path. You can do that, but I don't recommend that. Change your folder, and look what it does. It gives you a clean directory. Create a new folder to create a clean new directory to do whatever you want. And the gist of this. Look at that. You can create a matrix just like doing this. And then if you're a little lazy, for those who love copy paste, -1. And then look at that. Pretty cool stuff that you can see. And then you can do the the prime of this class, A, B, and you can do matrix multiplication. So if you know how to do matrix multiplication, this is how you do it. But one thing I want to tell you guys, if you're trying to test this and play with it, add a dot. This function right here, there's a couple functions I want to talk about before we even start this. This right here is scalar multiplication. So if you wanted to multiply this times this, actually it's more easier if I show you the minus sign. Let me do this. Actually, no, let's do it like this. There we go. Yeah, let's do 4. There we go. There we go. So I instantiated 2 little vectors. So here's a 1 by 2 and or 1 by 2 matrix, 1 by 2 matrix. If you wanted to multiply this to this, this to this, etc., you can use the scalar option, which basically does what you want it to do. It takes a couple elements like this and another set of elements and then just multiplies right on top of each other. If you wanted to do matrix multiplication, what happens when you have a 2 times 1 times a 2 times 1, 2 by 1 by 2 by 1? It won't work because, and I'll show you, because it's matrix multiplication, you need to make sure you have 2 by 1 by 1 by 2. You have to make sure the matrices are compatible, and you can see that right here. If you hover right there, I can't show you, there's my mouse. You can see a 1 by 2, 1 by 2. If you wanted to invert a matrix or rotate or transpose is the word, all you got to do is just do a dot and this little apostrophe, and this will flip it. Actually, I'll run this one. You can do F9. I like doing that. And then if you do this command, F9, it flips it for you. So now we have a 1 by 2 matrix multiplied by a 2 by 1, which gives us a 1 by 1 matrix. So that's all I wanted to show you for this quick introduction. Now let's get to the big part of this. So how to use this to solve practical problems. So one of the problems I wanted to show you is this circuit right here, and you've probably seen it. 0 to 3. Let's do an inductor, and let's do R is equal to 1.5K, and L is equal to 15 henries. Here we go. Oh, gotta ground this. I know some of you guys are pesky about that. So we're just gonna do a simple circuit. We're gonna try and solve this using the Laplace transform, and this one basically is a pulse from 0 to 3. We're gonna have 10 microsecond delay, I don't know, 10 pico rise time, 10 pico fall time, and it turns on for around 60 micro, and it repeats. So this is a problem. If you wanted to know where I got that from, I got that from here. So this is a previous homework. And yeah, I'm right on the dot. Oh, should have been nano, but pico and nano, same thing, very, very fast. So let's solve this little circuit. If you guys are like, oh gosh, I don't know how to do this, we're gonna try to solve for this circuit for a full amount of time for both the rising edge and the falling edge. So for analyzing this circuit, actually, let's give it the initial condition of the inductor at time is equal to 0 is equal to 0. We're just gonna say, okay, our source is off, it's not doing anything, we just have literally an LR circuit. So to start, okay, let's get this right there. Go full screen. Let's do a voltage divider. We're gonna solve for the voltage right here, which is VL. And let's grab a new marker. There we go. So what do we know from voltage dividers? The output voltage, we'll do it as a function of S, which is equal to the input, and then the voltage is going to be R, and then R plus SL, but we wanted to get into a form where we can get poles. I like calling them poles. Vn R divided by L S plus R divided by L. Pretty cool, eh? But we want to do something cool with the input. You notice that the input's this nice little thing. We'll notice that our input, the in, is going to go, here's 10 micro, and then we have it hold for 60 micro, which means 70 micro is when it's going to turn off. There we go. And that's what we want to do. We want to simulate this. So from that one homework where we asked you to, all right, look at this pulse and then give us the actual pulse in terms of unit steps. So if you haven't noticed, okay, we're 0 here, and then we turn on our unit step. Turns on at t minus 10 micro. Okay, and now we're turned on, but we got to turn it off. So that means we got to do minus 3 u of t minus 70 micro. And that's our input as a function of time. Now we want to go into the Laplace transform. So you already know that, which is 3. And yeah, I was picky about this. S 10 micro divided by S minus 3 E minus S 70 micro. And I like writing it like this, S minus S 10 micro. I always put the S in the front so we can see that. So this is the input that we're going to be using. All right, so the next step is we got to multiply this guy to our nice filter. This is going to be S is 0, which means it's going to be a low pass filter. There we go. And why I say low pass, take this S to infinity. S, the frequency, very fast. This term gets really, really big, which means this thing is going to be 0. 0 times your input, always going to be 0, which means at high frequencies, it's 0. At low frequencies, it's 1. Low pass filter. Oh yes, Dr. Baker always does this. There we go. So grabbing a new piece of paper and writing everything down. VL as a function of S is going to be equal to, let's write our actual filter, S plus R over L. And yeah, let's do it like this. E to the minus S 10 micro minus E to the minus 70 micro. There we go. And we got to do quick multiplication, which is equal to, we're going to multiply this to this. So this whole chunk gets multiplied here. This whole chunk gets multiplied here. If some of you guys can't see this, treat this as like a, well, not a constant, but treat this as it multiplying to this, and then it multiplying to this. So I'm going to do a crazy trick right now. No tricks, no magic. You like magic? No. Good. Let's do A S plus B of S plus R over L. And this is all multiplied by E to the minus S 10 micro. So one thing that some people were not getting correctly right is, oh, where are they supposed to put this E to the minus S? Treat this as a constant. It's multiplied to the entire thing, so this is going to go on the side. So what we're really focused on is just the poles. This has a pole at 0. This one has a pole at minus R over L. If you were to draw the Laplace transform of that. Minus, actually, let's, do I want to put a minus sign? We'll put it later. Actually, we know it's going to be minus, so C S plus D, there we go, plus R over L, E to the minus S 70 micro. And what we're going to do is the Heaviside theorem. So the Heaviside theorem, well, what Dr. Baker's been doing all this time is basically, if you want the A coefficient, you look at this bad boy right here. Well, this term right here. We're going to get rid of this S term, and then we're just going to look at this pole right here at S is equal to 0. So if you don't see that, how do I make you see that? We're going to look at this term. Let's get the green marker. Okay, so this term right here. Okay, so to solve for the A coefficient, we got to get rid of this. We're going to ignore this S for now, and then we're going to for s is equal to 0, we're going to solve for this, which is this r divided by L. How do I want to do this? R divided by L, 0 plus R divided by L times 3. There we go. Which is equal to, well, 3. That's our A. And then consequently, our B, so we're going to look at, well, get rid of this term, and the pole for this one is at minus R over L. So that means we're going to replace this S with minus R over L, which means we're going to get R over L, 3, minus R over L. It's going to get us minus 3. There you go. And if you see a pattern, and that's the reason why I wrote it like this, see how these poles are the same, and I just moved this minus sign right there. So if you wanted to solve for C and D, it looks like a mirror image. Like, look at the poles, look at the coefficients. I pulled up the minus sign so it all makes sense. You can consequently say that this is also equal to C, and this is also equal to D. There we go. And therefore, our final coefficients, VL as a function of S, is equal to, I wanted to write it under. It's okay. I'll write it like this. 3 S minus 3 S plus R over L e to the minus S10 micro minus 3 S minus 3 S plus R over L e to the minus 10 S70 micro. There we go. And knowing our final product, do I want to use a yellow marker? You guys will love it, right? No. Alright, it's okay. VL of t is equal to, this is a unit step, but this unit step's delayed. It's going to be 3. Actually, we're not going to even delay it. We're going to do something cool. 3 minus 3. This is a pole. Well, it's an exponential. So it's going to be e to the, and this one we have to delay, t minus 10 micro divided by, let's see, if we set tau is equal to L over R, which means this term right here is basically 1 over tau. There we go. That's how you do your time constants. You can also do R divided by L right here, but I kind of like keeping tau like this. It's a nice way to see it. Unit step, t minus 10 micro minus 3 minus 3e to the minus t minus 70 micro divided by tau, u of t minus 70 micro. Go. And now you're like, hooray, we got the answer. You forgot one more thing. Actually, let me see the actual quizzy. There we go. If you wanted to get the input, actually, here we go. This is the problem I was looking at. The voltage across. Some of you guys are like, oh, I'm just going to solve for whatever I see. You got to read the question first. If it's asking for voltage across of the inductor, then you can switch it here. Then you got to do the whatever's on this side, V plus minus V minus. In this case, it's Vn minus VL. Therefore, let's get back to here. Oh, come on. If I were to show you, there we go. Vn as a function of time is equal to 3 unit step t minus 10 micro minus 3 unit step t minus 70 micro. And we already know this input here. Let's see. So we see that, let's grab this black marker. What's common with this? You see this 3 right here? And you see that right there? Therefore, this right here matches with this guy right here. And then let's bring out red marker. That's kind of red. This guy right here cancels out with, actually Does that cancel out? I don't think so. No, because we're doing Vn minus, okay. Vn t minus Vl t. There we go. So this is going to be minus by this. 3 minus 3 is going to be 0. Well, 0. And then this right here, this minus 3 is going to be minus by minus 3, which is also 0. So minus 3 minus minus 3 is going to equal to 0. So all we're left with, actually, let me just highlight this one. This one belongs to this one. So all we're left with is this. So Vn minus Vl, this right here is going to turn into a plus 3 e to the minus t minus 10 micro over tau unit step. Don't forget that unit step. You guys are going to get docked off. Just kidding, no. Minus this one. So minus Vl cancels this one, and then we get that minus right there. E to the minus t minus 10 micro tau u of t minus 70 micro. And there you go. That's our final equation. And now you're saying, all right, how do I put this into MATLAB and verify our answers? So that's the next step we're going to try and do. There we go. So I already have a script already kind of running. So the first thing we need to set up is, okay, let me just pull this guy out. Copy, paste. Oh yeah, so we're going to have our time interval. We're going to go from 0 to declare a time. Well, you declare this vector right here using these brackets. I'm going to go from 0 to 100 micro. This is the micro symbol. If you wanted milli, you can do e to the minus 3. But we're doing e to the minus 6. There we go. And the precision, this is our precision. We're going to go in 0.1 microsteps. So that's our time. So the next thing we got to do is I want to set up some delays. And copy paste. There we go. So our first delay is going to be at 10 micro. The second one's going to be at 70 micro. We're just declaring variables. This is how you declare variables. To declare the unit step, there's a function called the ones function. If you want to know anything in MATLAB, and this is a great tip, help ones. You can do any function. So this right here is a function. It's a predefined function. It's already installed with MATLAB. If you want to know any of the other MATLAB functions, you can go to mathworks.com to figure out all these functions. There's a lot of functions online. But if you wanted to know what's going on, okay, ones, we're doing so here's another function, length, the length function. Help length. There we go. It just returns the size or the size of a vector, whatever our input. Here's our input. We're going to try and get the size. We're going to try and get how many points there are, because we're in Excel. It's we got to figure out how many vectors or how long this vector is. However long this is by one column. So a bunch of rows and one column. And let me see if I can post this. Actually, let me do this. Actually, okay. To create a figure. So we're going to create a picture. So if you ever want to plot something, you use the figure function. And this number right here just basically means, oh, what figure number are we on? So figure 1, plot. We're going to plot. We want the x-axis to be the time. And then our y-axis is going to be the unit step. We're just going to do this. So make sure they're the same size. So this one right here is, so let's run this. There we go. Is it doing what I want it to do? Oh, no, that's not it. It's because I gotta show you this other function I created. So I created this quick function to mimic our unit step. There we go. So this is where you CPs or EEs who are pretty curious can go crazy with MATLAB. You can do a lot of cool things. So right here, I'm doing a while. So I instantiated all the unit step to be completely 1, as you can see right here. Okay, figure 1. Oh, that's how you instantiate a picture too. but I want to plot this one. There we go. Oh, what was that? So we're just creating a vector of ones, as you can see. It's 1001 points long. So what I'm doing is literally looking at while a vector or value k is less than or delay, and then just force it to 0. This is a weird way of doing it, but it's the way that works. And then I will run section, and then boom, that's our unit step. And for those who have OCPD, title unit step 1, and then x-axis time. There we go. There we go. X-axis. Oh, X label, sorry. There we go. Yeah, you'll hear that beep a lot if you make a bunch of mistakes. So there we go. Our unit step right here. Let me bring out one more function. This right here is a helpful function. This right here sets up our x ticks and y ticks. There we go. So this function right here is, oh, look at our x tick values, our time values at this number, and this number, and then at these numbers. So this one, let's label this guy to this one. So that's what I did right here. And you can see here's a 10, and then if I wanted to do 2, there we go. Boom. Ah, I see. And then if you wanted to create another figure, because you have OCPD like me, just kidding now, 2, and then let's call this one 1, run section, boom, here's our, no wait, there we go, boom, there we go, unit step 1 and unit step 2, hooray, we got that one ready. So now the next thing we gotta do is actually do our mathematics. So if you don't mind, I'm going to do a lot of copy and pasting because we're reaching, I think, the 30-minute mark. I didn't want to make this video too long. There we go. We instantiated a new variable L, which is 15 milli, and then our resistor, which is 1.5 K. E3 is K. Here's our tau, V in, and here's our V out. However, actually, I'm not going to call that V out. I'm going to call this VL for consistency. And let's do CLC. That clears the command window. So all I did was punch in our actual vector or actual function. So as a calculator, 3 minus 3, actually, we have the power to do this. There we go. Oh, there we go. So what we're doing is, all right, we're doing 3, this is 3, minus 3, and then here's our exponential. This is how you write exponential. You can't do E because it treats E as a vector. So you have to do exponential if you want to know what it does. Help exp, and it just does this complex mathematics. Parentheses, this is a function. Minus t, 10 to the t minus, here's our t delay. Actually, you could have done this. Delay 1. So here's a huge tip for you programmers or who want to keep everything consistent. It's good to keep a lot of variables. Use a lot of variables. Don't use hard code. Actually, if you wanted to, you could have actually done something crazy. Actually, do I want to do that? Nah, it's okay. I was gonna say you can also make this 3 a variable 2. You can change your voltage source. Actually, okay. There we go. Because what am I gonna do is I'm gonna change this voltage. The voltage, VDD. There we go. Is equal to 3 volts. And multiply 3 times, and then 3 times. There we go. So there are 3 values stuck in there, so that's what we do to keep our stuff consistent. Tau, and then minus, and then same thing, copy paste, and then you can do delay 2. So now we can actually do some more crazy stuff. I'll show you. And there we go, our unit step 2. We got to use the scalar multiplication because we're trying to do this. We have a couple data points here, 5. We have 5 right here, and then we want to mix them together like on top. If we do matrix multiplication, if you forget this period thing, you're gonna get like, oh, instead of it doing this, it's gonna multiply like this, and it's gonna that's not good. You'll cry. So, and yes, you'll cry a lot when you're using MATLAB. Be prepared for a 360 if I were to teach it again. But we're gonna plot our input Vn, and then we're gonna plot VL. There we go. And is that exactly what I have? Nope. Let's do more stuff. What other hidden stuff do I have to show you? All right, let's see the new code that I just copy pasted. The subplot function. So I'm gonna instantiate a new picture. We're gonna make the picture have 2 little plots. So the subplot function, if you want to know what it does, help subplot. You can read all about this, like, oh, what it does. And it does cool stuff. 2 rows and 1 column in position 1. The time, the input, we're going to color it. I like to color it. Change the line width and titled it. And this is the input. Input. There we go. And then xticks, pretty graph. And you're probably saying, is that a function in MATLAB? No, actually, you can create your own functions just like in C++. If you've already taken, what do you call it? 135, CS 135, so you'll be ready for this class. Everyone's asking, why do we need 135, CS 135 for EE221? This is the reason why. Just kidding, no. But you can apply everything that you have. Actually, MATLAB's based on Python, so if you know a little bit of Python, be my guest. You don't have to do these, no semicolons. You'll get used to it. Actually, see this right here? It needs a semicolon. Let's fix that. Semicolon. Now we have clean. Actually, what's this? It says, oh, it doesn't like brackets. It wants this. There we go. And now you have a clean bar. No warnings. Clean. Now let's get to the puppy of this. Unrecognized. Oh, that's because I gotta plot VL. There we go. Boom! Look at that puppy. And there you go. This is how you prove your hand calculations. Instead of, okay, you could actually, you could do this where you have, here's your VL of t. You can punch in t is equal to any value, and then you can just by calculator, or you can use MATLAB as a way to prove your results in LT-SPICE. I already assumed that everyone knows how to simulate this in LT-SPICE, but that looks like something we can do. And then let me get to the fun part too. Actually, we haven't actually answered the question. We want to know V across, which is basically Vn minus VL. There we go. And then let's create another figure. You're gonna love this class. Figure 2, V across, and let's call it let's make it green. Voltage across. Font name, Comic Sans, and boom. Oh, don't like that. There we go. Run it again. Boom, there you go. Actually, if you wanted to make it more prettier, you can do, okay, Y label voltage as italicized V, V, remove, there we go. Boom, and now it looks more professional. Let's go. X label time in micro. Backslash mu gives you the mu sign t. There we go. Oh wait, not mu t. S. There we go. There we go. And that's something you can copy paste and put that in your homework and be like, oh wow, we understand what's going on. CLC. Boom. So that was a small tutorial on how to use MATLAB. You probably won't do anything crazy. If you wanted to prove your hand calcs like this, be my guest, go ahead. It's a good learning experience. If you're an EE, I recommend getting MATLAB because you'll be using it a lot through a lot of classes. If you take signal processing, you're definitely going to use it a lot. I use it all the time in grad school. Actually, let me show you another fun thing. The reason why I made these functions. Let's say our thing is too fast. Let's make it 40. Our pulses are too close to each other. Oh, look at that. Oh, you see that? Looks pretty cool, eh? So let's make it even closer. 20. Oh, you see? We can do a lot of crazy things when you have MATLAB, or when you create a bunch of variables. You can do a lot of things like, oh, you wanted to see how your circuit worked when you do this kind of pulse. Like, look how short that pulse is. Like, you can actually see what's going on. And yeah, it's pretty cool. I wish I can show you that stair step. I think I could. I don't think so. Or maybe I could. No, because this is V out and you have to recalculate it again. It's okay. But that's how you use MATLAB, and hopefully you can use this more to do some other stuff. Actually, if you wanted to make it pretty, you can EE221 homework or quiz something, or exercise. There we go. And then you can create a lot of sections. There we go. So if you wanted to publish this, you can publish it into, there we go. I like publishing it to a PDF. Go, so that we can publish into a piece of paper. Oh, it's gonna do that glitch again. Oh, there we go. Exercise. There we go. Beautiful graph. Here's our figure 1. Here's our figure 2. You can staple this to the back of your paper if you wanted to, and boom, there you're done. That's how you do it. Actually, okay, you want some more advanced stuff? You guys can see that in 360. All right, y'all. Have a good night and take care.